last class, we talked about the angular velocity, which is defined as the rate at which the angular position of the object changes. The angular position of an object, for instance, a rotating plate whose plane is placed on the board, that object can also be called laminar object. Lamina means plate wise or plate like. When you draw a straight line inside the object on the plate, that straight line makes an angle, say theta with respect to the fixed line, x dash and x. When this theta changes, we can say that the body is rotating. At what rate this theta is changing, that is the angular velocity of the object. This is the plate of any size and shape. Plate or lamina. If theta increases, omega is positive. Positive omega means anticlockwise rotation. If theta decreases, the body will have to rotate in this way. Clockwise rotation, theta decreases, omega becomes negative. Negative omega means clockwise rotation. Anticlockwise, and this is clockwise. That is what I explained in last class. This is anticlockwise rotation. This is clockwise rotation. Here theta increases, here theta decreases. So the concept of omega is derived or defined or explained or expressed by taking the straight line, drawing on the rigid body, and measuring its angle of inclination with respect to a fixed line which is fixed with respect to ground. Therefore, this measurement of angular velocity is based upon the method is called ground frame method. That is what we discussed in the last class. In this class, we will talk about the angular acceleration. In linear quantity, we have linear velocity and linear acceleration. Similarly, in angular quantities, in angular motion, this is the linear motion. In linear motion, we have linear velocity and linear acceleration. In angular motion, we have angular velocity. Similarly, we have angular acceleration. Linear acceleration is defined as the rate of change of linear velocity. Similarly, the angular acceleration can be defined as the rate of change of angular velocity. Since linear velocity is a vector quantity, its derivative must be a vector. Therefore, acceleration is a vector quantity. Linear acceleration is a vector quantity. Similarly, since angular velocity is a vector quantity, as you defined, because angular velocity has some magnitude, so also the direction is anticlockwise, which is given vectorially in positive z axis. If this is x, this is y. When it is clockwise, it is given or it is pointing in negative z direction. Therefore, omega is a vector quantity as it is endowed or associated with both magnitude and direction. Well, the rate at which the omega is changing is defined as angular acceleration, and we have to talk about this angular acceleration especially in this context. Well, to define the angular acceleration, we need to take this rotating plate. Let the plate rotate in anticlockwise sense with an angular velocity omega. If omega changes, if the angular velocity changes, the rigid body, this is the plate in this diagram, is said to have an angular acceleration given by alpha is defined as the rate at which the angular velocity is changing. The rate of change of angular velocity is defined as angular acceleration. We can compare it with the linear analog. The rate of change of linear velocity is defined as linear acceleration. We studied in translation, translatory motion, and in rotary motion or rotation or angular motion, this angular quantity called angular acceleration can be made equivalent to or can be made analogous to the quantity, the acceleration we are using in translation. Therefore, it is called linear acceleration. Linear acceleration, and this is called angular acceleration. This is called linear velocity, and this is called angular velocity. Linear acceleration is defined as the rate of change of linear velocity. Linear acceleration is equal to rate of change of linear velocity. We talked about this matter, or you would have read this matter in kinematics of a particle. Or translatory motion. Translation is used for a point mass or particle or the point, whereas rotation is used for a straight line. Rotation word cannot be used for a point. The angular motion or rotation can be used or is used for a straight line, whereas linear motion or translation is used for a point. Rotation of a point has no meaning at all. Rotation or angular motion of a point or particle is meaningless. When somebody will tell you the particle is rotating, it has no meaning. Rotation of a particle has no meaning. Translation of a particle has meaning. When you say this particular point is moving in this can be called translation of a point, but not, it's not rotation, it is a translation. So when you talk about the rotation, we need to draw a straight line. This is a straight line. When it changes its angle of orientation with respect to ground, it is said to be rotating. So when you try to define rotation, you need to take a straight line. But when you take a point and try to concoct the philosophy that when the point is moving in a circle, or the point is moving in a parabola, or the point is moving in a straight line, or it may be moving in any curve. When the point moves in a curve, you cannot call it a rotation. This is meaningless. So the motion of a particle or the point mass or a point is not rotation. Then what is this? When the point moves in a circle, you may think that it is rotation. It is not rotation. It is a circular motion. When the point moves in a parabola, it is called parabolic motion. When I throw an object, this is tracing a curve, that's parabola. This is called parabolic motion or projectile motion. When the point moves in an ellipse, say the planets revolving around the sun, the planet sizes are negligible compared to the distance between the sun and the planet. Therefore, the planets can be treated as particles. They move in the path we cannot call the planets are rotating in this way. The planets translate when you take the planet as point mass. However, the rotation of the planets can also be taken into account when we assume that planets are not point, they are some spheres. They can rotate. A cylinder can rotate either in this sphere or in this sphere or any way it can rotate. So when something is rotating, we will take a straight line in that thing. When something is translating, we talk about translation. Then we have to say which point is translating. It may be x point or y point or z point or point 1 or point 2 or any other point, or center of mass is also a point. And next section I will tell you, when the center of mass has some velocity of any rigid body, we can say that rigid body is translating. So whether the center of mass is moving or not, if it is moving, the body is said to be translating. If it is not moving, then we can say the body may be rotating. All these things in the next context we can discuss in the types of motion of the rigid body. So coming to the original discussion of the angular acceleration, which is analogous to the linear acceleration. Since linear acceleration is defined as the rate of change of the linear velocity, angular acceleration can similarly be defined as the rate of change of the angular velocity. Linear velocity is a vector quantity. It has both magnitude and direction. Either its magnitude changes or its direction changes or both. Then only you can say that the particle has, or the point mass has, or the point has some linear acceleration. Similarly, angular velocity is a vector quantity. It has some magnitude. Its unit is radian per second, 2 radian per second, 3 radian per second, 10 radian per second. These are all the magnitudes. When it rotates in anticlockwise manner or clockwise manner, that gives us the direction. Anticlockwise manner, generally it is a positive z axis, a z direction. Clockwise manner, it is negative z direction. Similarly, we can have the change of the angular velocity just like the change of linear velocity. Look, linear velocity has both magnitude and direction. Angular velocity has also magnitude and direction. When the magnitude portion of the angular velocity, that is the angular speed, or the direction portion of the angular velocity, that may be clockwise or anticlockwise or plus k cap or minus k cap, or plus I cap or minus I cap, or plus j cap or minus j cap, or combination of all arbitrarily. When the body rotates, it has some angular velocity. When it rotates like this, it is angular velocity. It is governed by right hand thumb rule, as I discussed in the last class. When that direction part changes, also the body is said to be having the angular acceleration. Let us assume that the particle moves in a circular path. When the magnitude of the velocity vector, that the speed of the particle, remains constant in the circular path, that particular motion is called uniform circular motion. Magnitude is not changing. When the magnitude of the linear velocity does not change, you cannot say that v is constant, v is not constant. In circular path, In circular path, this point velocity changes from time to time by magnitude or in direction. If you can keep the magnitude constant, the direction part is changing because the line of motion, the line of inclination or the angle of inclination of this vector, velocity vector, keeps on changing. Therefore, its direction is changing. Because of the change in direction, another acceleration comes into play, and that acceleration is called normal acceleration or centripetal acceleration for circular motion. Similarly, when the direction part of the angular velocity changes, also the body is said to be having an angular acceleration. For instance, this body is rotating like this or rotating like this. When it rotates in anticlockwise manner, this is the extended thumb is representing the angular velocity direction. This is outward, or this is anticlockwise, or this is along positive z direction. If you take this is x direction, this is y direction. Well, when it is rotating in anticlockwise manner and I am twisting my hand, even though I am keeping the magnitude of rotation, the angular velocity constant, I am changing its direction part. When the direction part is changing, keeping the magnitude part of the angular velocity constant, the rotating object is said to be possessing an angular acceleration. But while doing so, the axis of rotation or the axis or the direction of rotation or the direction of the angular velocity changes. Or when both magnitude and direction of the angular velocity change, the body is said to be having the angular acceleration. One by one, let us discuss. Well, angular acceleration is the rate of change of angular velocity. Let us assume that this body is rotating in anticlockwise manner in the plane of the board. Here I restrict the direction of angular velocity to a constant value. The direction of angular velocity is not allowed to change. Then I can write omega is equal to its magnitude times the direction, that is outward or positive z direction if I take this coordinate axis. The rate of change of angular velocity is defined as angular acceleration alpha, can be given as d omega by dt. Omega vector can be written as omega k cap. Here, what is the assumption? Assume that the direction of omega vector or angular velocity vector remains the same. In other words, the body, or for the sake of simplicity, the plate keeps on rotating in the plane or parallel to the plane of the whiteboard. In some sense, in anticlockwise sense. Under this assumption, so long as it is moving in anticlockwise sense, the KKF, the direction remains constant. And direction remains constant, take the direction, the constant part, this vector quantity out of the derivative. So we are getting just the derivative of the magnitude of the angular velocity or the angular speed. Now we can call it alpha. This may give us some wrong impression. This may give us some wrong impression. This quantity we are getting, no doubt alpha vector is the angular acceleration. But this is not complete alpha. This is the alpha, this is the angular acceleration based upon this assumption. Assumption is that the body angular velocity direction remains constant. The direction of angular velocity of the body remains constant. That's the assumption. So this is based upon the assumption that the direction of omega remains constant, remains the same. This means that the body or the plate keeps on rotating in the plane or parallel to the plane of the whiteboard in anticlockwise sense. So alpha will be in which direction? Alpha will be in positive z direction, but we need to expand it. Alpha is equal to, under this assumption, alpha is equal to d omega by dt kk. We have two division. If the magnitude of the angular velocity, the angular speed decreases, suppose it is rotating with 10 radian per second, after some time it will rotate with 8 radian per second. What does it mean? It's the initial angular velocity, this is the final angular velocity, or this is omega 1, this is omega 2. You can write 1, 2, or you can write I and f for initial and final respectively. When the angular velocity decreases, what happens? Let us see. When omega decreases, d omega by dt, the difference is negative. Therefore, alpha is equal to negative of d omega by dt. Alpha points in negative z direction. Under this assumption, alpha or the angular velocity, angular acceleration must be directed in opposite direction of omega. Omega is anticlockwise or positive kk. Alpha is clockwise or directed in negative kk or negative z direction. So if omega is anticlockwise or outward or plus kk direction, alpha direction is clockwise or inward or in minus kk direction. Anyone you choose, you can choose this symbol, or you can choose this symbol, or you can choose this symbol. This means that alpha vector is anti-parallel with omega vector. Alpha vector is in, omega vector is out. Alpha vector is in, omega vector is out. Both are anti-parallel. This is one case A. If the angular speed increases, suppose initial angular speed is 10 and the final angular speed is 12. After few seconds. Then the angular speed increases. If omega increases, d omega by dt is positive. Then alpha is given as or is directed along which direction? Positive z direction or plus KAB direction. Therefore, we can write that both the vectors are parallel. Suppose omega is anticlockwise, omega increases when you use the word increase or decrease, that is always imply the magnitude, increment or decrement, increase or decrease. Words are used for the magnitudes only. When omega increases, d omega by dt is positive. Therefore, alpha is equal to d omega by dt, KAB is positive. Positive means it's directed in positive z direction. Therefore, alpha is either outward or anticlockwise or directed in positive z direction. Therefore, or in other words, we can say that alpha is parallel to omega. In this case, omega increases. In this case, omega decreases. d omega by dt is negative. Therefore, alpha is equal to d omega by dt minus KAB. Our alpha vector is antiparallel with omega vector. If omega is positive or outward, alpha is inward. Here omega is outward, alpha also is outward. So these are the direction. The direction of alpha is controlled by the rate at which the omega is changing. Change, when you use the word change, it may decrease, it may increase. Both decrease and increase can be called change. The direction of alpha is controlled by the change of omega. But here the direction part remains constant. The axis of rotation is kept constant. If of angular speed, if the axis of rotation is kept constant. This is very important to understand the relation between omega and alpha. Alpha is equal to d omega by dt. Without any vector sign also you can write like this. But remember, if omega decreases, alpha is negative. If omega decreases, alpha is negative. We can say that the body is decelerating, and this alpha is called angular deceleration. It's called angular retardation or angular deceleration. Deceleration what you can use, or retardation what you can use when the angular speed decreases for angular quantity alpha or angular acceleration alpha. For linear acceleration, when the speed decreases, the body or the particle is said to be retarding or decelerating. Retardation or deceleration term can be used when that quantity, that velocity, magnitude decreases. And if omega increases, alpha is positive. Positive means it's directed in positive direction, a positive z direction or a positive x direction or positive y direction. Alpha is positive. And we can call it angular acceleration, no problem. So omega increases, alpha is positive. Omega decreases, alpha is negative. Assuming that omega is pointing in anticlockwise manner, or it is rotating anticlockwise manner, or it is pointing in positive z direction. This is the assumption. Sometimes they may give you the examples. The conceptual example, say this is the disk. For the sake of simplicity, let us pivot it, and it is having an anticlockwise rotation. Theta, any straight line, radial line say for the sake of simplicity, makes an angle theta with respect to positive x direction is equal to 2t square let. When the straight line drawn inside the rigid body or the disk keeps on changing the angle of its orientation with respect to the fixed line, the body is said to be rotating with an angular velocity d theta by dt. Theta is in which direction? Yes, in which direction? Positive z direction. So you can just write vectorially. To take it out, d by dt of t square. So we are getting 4 kf into t. This is the angular velocity. Suppose at time t equal to 1 second, put t equal to 1 second. How much? 4 kf radian per second. Then what is alpha? Angular acceleration is equal to d omega by dt. d by dt upon how much omega you are getting? Function 4t kf. Take 4 kf out because you are not changing the axis of rotation or the direction of omega. You take 4 kf out, you are getting a constant quantity. Radian per second square is the unit of angular acceleration. Radian per second is the unit of angular velocity. Is the question. And if you take the same question, but you take the omega in which direction? Clockwise direction. To get a clockwise omega, suppose omega is equal to minus tau t k cap is given, or omega magnitude is given. Let magnitude of omega is given as 2t. Find alpha. Our basic formula is alpha is equal to d omega by dt in vectorial form. d upon dt, omega vector is equal to how much? Tau t. In which direction? If you take this x direction, this y direction, this will be negative z direction or minus k cap. Take minus 2 k cap out, you are getting a constant quantity radian per. So the alpha will be in same direction. Therefore, alpha is parallel to what? Omega. If omega increases, when omega is out, alpha will be out. When omega is in, alpha will be in. When omega is along positive z direction or positive x direction, alpha will be in positive x direction. When omega is positive y direction, alpha will be in positive y direction. When omega is in positive negative y direction, alpha also will be in negative y direction. When omega increases, alpha will be unidirectional or parallel to omega. Alpha and omega are parallel when omega increases or the angular speed increases. When the angular speed increases, the angular velocity and the angular acceleration are having same direction if the direction of angular velocity remains unchanged. Let us take another example. The example is this disk of radius r is equal to say 1 meter, spins. Another name of rotation is spinning. It spins about its center of mass with an initial angular velocity omega naught. Suppose is 2 radian per second. And alpha is in opposite direction. This means that the disk is retarding with an angular acceleration that's equal to a positive constant times the square root of the angular velocity. Alpha varies with respect to omega in this way. Alpha varies with respect to omega in this way. Assuming radius and angular velocity initial 1 meter and 2 radian per second respectively, find the average angular velocity over the period of its motion. Since it is retarding, sooner or later, today or tomorrow, it will stop. The time of rotation we need to calculate. And initial angular velocity is given. What is the total angular displacement or angular distance that we need to also calculate? The average angular velocity is given as total distance, angular distance upon the total time, where theta is the total angle described or rotated by the disk, and T is the total time of motion or rotation. This formula is analogous to the formula for the average linear velocity is equal to net displacement by the time interval. Using this equation given in the question, we need to find the total angular distance the disk spins, the disk undergoes, and the total time of rotation of the disk till it stops. The given condition is that alpha is equal to k into square root of the angular velocity. That is not initial, that is a functional value which gives the instantaneous value of the angular velocity of the disk, and this is the instantaneous value of the angular acceleration of the disk. Since the disk is retarding, alpha can be written as minus d omega by dt. That's equal to k into square root of omega. Separate the variable now. D omega upon square root of omega is equal to k into dt. Now we have to integrate both sides. Integrating both sides at time t equal to 0, its angular velocity was omega naught. After time t, it will stop. Therefore, the angular velocity will be 0 in upper limit. This omega, you know that omega to the power half minus half d omega. The integral of this is equal to omega to the power minus half plus 1 by minus half plus 1. That's equal to square root of omega by 1 by 2. That's equal to 2 into square root of omega. So this integral value, after evaluating this integral, this will be 2 into the square root of omega minus omega naught to 0 equal to k into t. This gives us t is equal to 2 square root of omega naught upon k. This is the total time. Find the average angular velocity. Find the total time of rotation. This is the total time of rotation. Next, you need to calculate total angular distance covered by the disk till it stops. So, how much you got? The time of motion 2 omega naught 2 into square root of omega naught upon k. Equation number 1. Next, we need to calculate the total distance covered. Since alpha is equal to d omega by dt, multiplying in the numerator and denominator and omega. Omega dt we can just write d theta. Therefore, in terms of omega, we can get this expression of angular acceleration. Or alternately, we can write like this: alpha equal to d omega by dt. We can write d theta, d omega by d theta into d theta by dt. Multiply both numerator and denominator by d theta, and d theta by dt we can write it as omega. So we will get omega d omega by d theta. Same expression you are getting. So we have two expressions right now of the angular acceleration. Alpha is equal to d omega by dt in terms of omega and t, and in terms of omega and theta, alpha is equal to omega d omega by d theta. Writing alpha is equal to omega d omega by d theta, since it is retarding, you can put it negative sign, and alpha is equal to k into square root of omega. Using these two equations, we can write omega d omega by d theta, negative of that is equal to k square root of omega. This will be getting cancelled, and you will get square root of omega. Square root of omega d omega minus is equal to k into d theta. This is the separation of variables. Now let us integrate both sides. When theta is 0, omega is omega naught, and when it describes the total angle theta, it will stop, and the integration of omega to the power plus half is equal to omega to the power plus half plus 1 by plus half plus 1. This will come around omega to the power 3 by 2 by 3 by 2. This will be 2 by 3 omega to the power 3 by 2. This value you have to substitute here. Minus 2 by 3 omega to the power 3 by 2, lower limit omega not to upper limit 0, will k into theta. This gives us the total angle described by the rotating disc before it stops is equal to 2 by 3 omega naught by omega naught to the power 3 by 2 by k. This is equation number 2. So the total angular distance we calculated. When you get total angle and we got total time, taking the ratio, we can get the average angular velocity. The average angular velocity omega average is equal to total distance by total time. Total distance you are getting 2 by 3 omega naught into square root of omega naught by k by total time is 2 square root of omega naught upon k. This will be getting cancelled, k will be getting cancelled, total will be getting cancelled. You are getting a very cute answer, omega naught by 3. Answer is very beautiful question for all the entrance examinations you are appearing. So this gives us some practical utility of the formula of the angular acceleration with respect to time and with respect to the distance. However, we have another formula of the angular acceleration. Alpha is equal to d omega by dt, and we know that omega is again d theta by dt. Therefore, alpha can be written as the double derivative of the angular distance, d square theta by dt square. So we have one expression for alpha, second expression for alpha, and third expression. Let us recap all these expressions now.